Now that we've learned how ethers are formed using a dehydration synthesis reaction between two alcohols, it's time to take a look at the naming system of how to name compounds that contain an ether linkage. Now, as with every compound that contains a functional group, from alcohols to amines all the way up to carboxylic acids, it is the functional group that defines what the parent chain of the molecule is going to be. The problem is that aside from the ether, which is essentially a link between two hydrocarbon chains, there is no other defining feature here, and so we can default to the simplest rule that we have in identifying what the parent chain is, and that is simply by identifying whichever side of the ether has the longest carbon-to-carbon chain within the structure, which in this case is the B side of our molecule, because we can see that the right-hand side has 1, 2, 3, 4 carbons, and therefore our parent chain would be butane, whereas the left-hand side only has 2, which would be an ethane molecule. So as the longest carbon-to-carbon chain here, this would be a butane. Now, to indicate the presence of an ether linkage, remember that an ether is simply one hydrocarbon joined to another hydrocarbon via an oxygen intermediate, and so we can add an infix, which is a prefix that actually goes in between two words of oxy, in order to show that the F is linked to the butane via an oxygen that we see here. So we would simply call this F-oxybutane, like so. The problem is, if we take a look at this molecule below, we can see that the parent chain of this molecule here also has 4 carbons, and we also see that it is connected with a 2-carbon long side chain that is linked to the butane via oxygen, so this would also be F-oxybutane. The only difference between the two is the carbon number where the oxy or ether linkage is. So we would call the top molecule here 1-F-oxybutane, whereas the bottom molecule here would be called 2-F-oxybutane, with the number here acting as a location indicator. Now, when we get to a larger and more complicated structure like this, effectively we can think of this oxy, or the smaller hydrocarbon being joined to the parent chain, as just another side chain here. So if we count the number of carbons, 1, 2, 3, we would consider this to be prop-oxy in this case here. So this prop-oxy we can see falls on carbon number 1, so this would be 1-prop-oxy, and then the rest of this molecule we would name as per usual. So on carbon 1, 2, 3, we have 2 bromos, so this would be what we call 3,3-dibromo, and then we see on carbons, actually I have fallen into my own trap, carbon 1 is here, and we can see that our bromos are not on carbon 3, but in fact are on carbon 4, because I ignored carbon 1 here, thinking, well, I don't know what I was thinking here. But now that we have successfully identified where carbon 1 is, the last of our side chains is going to be 2,3, and because there are 2 methyls, this would be dimethyl, and then the approach to ordering our side chains remains identical. Bromo comes alphabetically before methyl, comes alphabetically before propyl or prop-oxy in this case, and therefore we would label this as 4,4-dibromo as our alphabetically first side chain, 2,3-dimethyl as our alphabetically middle side chain, and let's make some space here, and then because P comes after M and after B, we would leave the 1-prop-oxy, indicating the side chain that comes off of our ether linkage here, and then finally we would list off the parent chain, which has in fact 5 carbons, so this would be pentane. So the whole name of these two ether-linked molecules would be 4,4-dibromo, 2,3-dimethyl, 1-prop-oxy, pentane, like this, where the smaller hydrocarbon that is linked via an ether is effectively just considered another side chain like this. In the next video, we'll look at how the naming system for esters works and how to consider which side of the molecule came from an alcohol and which side of the molecule came from an acid.